Hey, this chapter is on chemical bonds. So we are going to look at some covalent bonds, ionic bonds, metallic bonds, and we will look at, in covalent bonds, Lewis dot structures. Do you guys remember doing that in physical science? Where you put dots around we had to have 8 dots. 2 years. Okay, so we will be doing that. So chemical bonds is a mutual electrical attraction between nuclei and valence electrons of different atoms that bind atoms together. What's a valence electron? It's one of the outer shell electrons. So valence electrons are outer shell electrons. And how many valence electrons do atoms want to get to be stable? 8, right? So they want to be like a noble gas. They want to have the same number of electrons as noble gases. So we're going to be looking at the highest energy level. So like if it's in the 4p sublevel, it would be the 4s and 4p electrons of that element. That would give you the valence electrons. When you form a chemical bond, it always creates a more stable compound. Ionic bonds are electrical attraction between large numbers of cations and anions. What's a cation? What's an ion in general? It's an atom that has a charge. And a cation has a positive charge, and anion has a negative charge. Way you can remember that, cation has a T, which looks like a plus. Cation is a positive charge, anion is negative. And then covalent bonds, ionic bonds, since one electron or one atom takes an electron from another, it's gaining an electron, so it's gaining a negative charge, so it has an overall negative charge. It's left the other atom with one less electron, so it has more protons than electrons, so we have a positive charge on it. So positive and negatives always attract each other, so the positive and negative is forming that ionic bond. Whereas covalent bond, one atom is sharing electrons with another. So the electron is moving around one atom, two different atoms, sometimes equally, sometimes unequally, but it's being shared between the two. So to determine if a bond is ionic or covalent, we use electronegativities. And I have an electronegativity chart for you. So if you look at your chart, let's look at water. For water, there's a hydrogen and oxygen bond. So what we're going to look at is the difference in electronegativity. So the number underneath the element is electronegativity. So oxygen has 3.5, hydrogen has 2.1. So what would be the difference? 1.4. So after you find the difference, you look down here at this little part on the left, bottom left. 1.4 falls between 0.3 and 1.7, so that would make it a polar covalent bond. See how that works? You took the 3.5 minus 2.1. You'll be able to use this chart, always. Nope. So you find the electronegativities for oxygen and hydrogen, and you subtract them, and you get 1.4. So when you look down here, 1.4 falls within the covalent bond region. The polar covalent. So if it's 1.7 or less, you get a covalent bond, but you have two different types of covalent bonds. You have nonpolar covalent, which is when electrons are shared equally. So electrons spend the equal amount of times around both atoms. And then polar covalent is when there's an unequal attraction for electrons. And that unequal attraction just means that electrons are spending more time around one atom versus the other. So it's kind of hogging that electron from the other one, but it's still sharing. The electronegativity is from 1.7 to 3.3. It's ionic. And ionic bonds are always polar because there's always an uneven distribution of charge. One atom has actually taken away an electron from another. So we are going to, well, this picture here. So this picture right here, the nonpolar covalent, you can see the clouds are equal in size. That means the electrons are being shared equally here. And they're touching because it's being shared. One's not taking from another. Right. On the second one, this atom is hogging the electron from this one, even though it's still sharing, but it's spending more time over here. And then this atom has taken an electron from this atom in this picture. And that's an ionic bond. So we're going to use electronegativities to classify the different bonds between sulfur and the following elements. So the first one is between sulfur and hydrogen. So what's the electronegativity for hydrogen or sulfur? 2.5. And hydrogen is 2.1, so our difference is, so what kind of bond would that make it? Polar covalent. On a worksheet, I'd like you to write it out. For your notes, you can do whatever you want. And then this last question, it says, in each pair, which atom would be more negative? In order to tell which atom would be more negative, we're going to use the more electronegative atom, which would be what? Sulfur. So sulfur is more negative. I guess I should explain what the electronegativity numbers are that you see there are. They're telling you how strongly they attract electrons. And so if you have a really high electronegativity, that means it's going to attract electrons strongly. So if it's attracting electrons strongly, more electrons are around it, it's going to be more negative. If they have a smaller electronegativity, it doesn't attract them very easily. It's more likely to give up electrons. And so the small numbers are going to usually be more positive. Okay, and then the next one is sulfur and cesium. And sulfur is 2.5. What's cesium? 0.7. So what's our difference? 1.8. So what kind of bond would it be? Ionic. And which one's more negative? And the last one, sulfur and chlorine. Sulfur is 2.5. What's chlorine? 3.0. So we just need the difference. So what's the difference between them? 0.5. And so what kind of bond? And which one's more negative? Chlorine this time. Questions on determining those? We're going to do another example. The one with the higher electronegativity. So if we have chlorine and calcium, we just saw that chlorine's 3.0. What's calcium? 1.0, so what's the difference? 2.0, so what kind of bond is it? Ionic. And which one's more negative? Chlorine. Chlorine and oxygen. Chlorine's 3, oxygen is 3.5. Polar covalent. And oxygen is more negative. And then chlorine and bromine. .0 and 2.8, so our difference is 0.2, which makes it nonpolar covalent.
What happens if you get zero? Like say you got titanium. Like,
Well, those are both cations, so they wouldn't. But let's say you have oxygen and oxygen
sure.
bonded together, then you get 0 and it'd be nonpolar covalent. Nonpolar covalent if it's 0. Now, because it's nonpolar covalent, do we have a more negative atom? No, because the electrons are being shared equally, so we don't have a more negative, so you don't write anything down for one that's more negative. So questions on determining the type of bonds. Okay. Covalent bonds, if you have a covalent compound that contains all covalent bonds, it's called a molecule, and they're neutral also. And some examples are water, sugar, oxygen. Those are called molecules. Sometimes that term molecule is used incorrectly, like it will refer to sodium chloride as a molecule. Sodium chloride has an ionic bond, so it's not a molecule, it's actually just a compound. So you have to be careful of when you use the term molecule or not. The chemical formula will show the relative number of atoms in a compound. So like in water, how many hydrogens are there? And how many oxygens? Yep, 2 and 1. And then diatomic molecules, those are always molecules. These, what do you think diatomic means? 2 atoms, 2 of the same atoms. So there's 7 diatomic molecules that when they are by themselves, they will always form diatomic molecules as a gas. And those 7, there's 2 different ways we can remember these because you need to know them. We can start at element number 7, which is nitrogen, and then draw 7 on the periodic table. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine. But then hydrogen is just kind of a oddball out, kind of out there on his own. So we can either have those 7, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. Or you can remember the saying, I brought clay from our new house. Yep, Mr. Payne, I think, used that one. So up to you how you want to remember that. But so if you ever see like nitrogen gas, it would always be N2. Oxygen gas is O2. Fluorine gas is F2. It's not just F, okay? So all of those would be N2, O2, F2, Cl2, Br2, I2, and H2. They're always diatomic. And those diatomic molecules will always form nonpolar covalent bonds because when you subtract their electronegativity, you'll get 0. This is just showing how the nucleus and the electrons are attracted to each other from both atoms here, but the electrons are repelled and the nuclei are repelled, so that's how it kind of holds. It doesn't like get sucked all the way in, and it has some space in between the nuclei there. And when it forms a compound, there's energy released. And so we want the lowest potential energy, makes it the most stable. And right here at point C, we have the lowest potential energy, because this is our potential energy here. Just like from your desk to up here on this cabinet, there's less potential energy down here. You're more stable here. When you form these compounds, it's kind of like when you roll a ball down this valley. You roll it down, it kind of comes back up, kind of rotates back and forth till eventually it settles down at the bottom. Same with the atoms. They kind of start far apart, they come close, far, they kind of vibrate back and forth until they get to the lowest potential energy. So the bond length is the difference between two bonded atoms at their minimum potential energy. And those atoms are vibrating back and forth. But it all depends on what atoms that have combined. So they're far apart. As you get shorter, you have more bond energy. The bond energy is the energy required to break a chemical bond. So if we think of, let's say you're cleaning up your yard and you pick up a stick out of the yard. Is it easier to break a stick when your hands are far apart or when they're really close together? Far apart, right? So it takes less energy. You'd have less bond energy if your hands are far apart. A longer bond has less energy. Shorter bonds have more energy. It takes more energy to break them. So you can remember that. And the greater the electronegativity difference, the greater the polarity and the stronger the bond also. So the closer you get to that 3.3 in difference of electronegativity, the stronger the bond is. Because the more electronegative atom is going to hold on to those electrons stronger. I'm not going to want to read them up very easily. And I think this next slide I have an example. We're going to arrange the following bond in orders of increasing bond length. So if we have a long bond, are we going to take more or less energy? Less energy, right? So if we're going from shortest bond to longest, we're going to go from short bond would have high or low energy? High energy. So if we have a short bond, we'd have high energy. So what bond would be the shortest? HF. And then what would be the next? HCl, HBr, and then HI. Yep. Does that make sense to everyone? Okay, I don't know what my thing's doing, but I think that's all the notes, though. I think that's where we're going to stop. Let me see for sure what's on next, but I don't know what it's doing. The one thing I want to explain is on number 13. It says write a formula for an example of each of the following compounds. Instead of just writing a formula, just find two elements when they bond together would form those type of bonds. Okay, so everyone can have different answers. There's no necessarily one specific correct answer. Otherwise, they all should be self-explanatory. Okay, this will be due tomorrow.